Remember that we found an expression for the current density J, which was the electron number density times the charge of the electron times the drift velocity. And the idea is that the number density times the charge, this is the charge density, charge per unit volume, and then this is the length per unit time that is added to that volume. So that altogether gives us the box that we have the charge in, and we end up with that's the current in that quote-unquote box. And separately, we had found an expression for the electron drift velocity, which was the electron charge times the electric field over the electron mass times the average interaction time. And this was that quasi-Newtonian kind of here's the force divided by the mass and the acceleration times the time. So we get something like that. Putting those two things together, we get that J is this times this, which is the electron density times the charge squared times tau over the mass. Everything in green is intrinsic to the material. They're chemical properties of the wire. In other words, what is the electron density? That's set by the lattice structure of the wire. The electron charge, of course, is fundamental constant. The average time of interaction is also set by the geometry of the lattice of positives. And of course, the electron mass is a fundamental property. So all these things come from the chemistry, the atomic chemistry of the wire. So it kind of makes sense to lump them together. We define a property called conductivity, symbolized by lowercase sigma, which is material dependent, such that the current density is the conductivity times the electric field. As an aside, this choice of symbol probably explains why some textbooks use eta rather than sigma for surface charge density. That's a matter of taste. In physics, we often overuse some symbols, and you have to pick your battles, and this is where they chose that one. If we apply the same electric field to two different wires, there'll be more current flow in the one with higher conductivity, i.e. they conduct better, so it kind of makes sense. The units of conductivity, of course, would be the unit of J over the units of E, or the amp per meter square over the joule per coulomb, which is the amp coulomb times the joule meter square. But a joule is a kilogram meter square already, so this becomes meter to the fourth, meter to the fourth, meter to the fourth. So we end up with something like coulomb seconds over kilogram meters to the fourth, which is just awful. There'll be better ones coming along later. This is just terrible. It's often convenient to speak in terms of resistivity rho instead of conductivity sigma. And that's easy. The resistivity is 1 over the conductivity, or rho is 1 over sigma. So we're just inverting. We're saying something which is high conductivity has a low resistivity. It doesn't resist flow very much, and vice versa. As a result of the conservation of current, the continuity, the field inside a conductor is constant, so if there's a potential difference across two ends of the conductor of length L, we'd have an electric field, which is E is delta V over L, and thus a current density J, which is E over rho, which is delta V over rho L. Here we see an illustration when a potential difference creates an electric field inside the conductor, causing charges to flow through it, and the equipotential surfaces are perpendicular to the electric field, like such. This means that the current flowing through the resistor, I, which is just J times the area, is the area over rho L times delta V. That is, the current is directly proportional to the voltage. This is going to be very important here. So the potential difference is the pressure that moves the charge. This kind of makes sense. The harder we push, the more current we get, right? Remembering always that potential is like pressure and current is like velocity of water or whatever. The current also depends on properties of the conductor, both extrinsic, its length and cross-sectional area, and intrinsic, its resistivity, which is related to the quantum electron C. Usually we wrap all of those properties, the material properties, into one, which we call the resistance of that conductor, symbolized by R, and it's rho L over A. The SI unit of resistance is the ohm, symbolized by omega. I kid you not, it's because that is spelled, right? It's omega, but it's pronounced omega. And I kid you not, that's why that symbol is called that. And the SI unit, the omega, is equivalent to 1 volt per amp. Resistances in the kilo ohm or mega ohm are quite common. We've left behind the range where we can say, oh, it's all human scale. It doesn't really work out that way. Charges are too large, and now resistances are very large, and so on. Not a big deal, just we'll often be working in kilo ohms or mega ohms. Putting all of that together, we get what's called Ohm's law, which is why it's called the ohm, which is that the current is the voltage divided by the resistance. which is known by engineers for generations as delta V equals IR. Or usually, in fact, most engineers don't even have the delta, and they just say the voltage drop is IR. Okay, wire 2 is twice the length and twice the diameter of wire 1. What is the ratio of their resistances? Well, we have that L2 is twice L1, and we have that A2 is twice squared A1, because of course it's the radius squared, or 4. So since our resistance is the resistivity that we're not changing, times the length over the area, we end up with 1/2. Probably should talk a little briefly about where these things are coming from. It probably makes sense that making the wire longer increases its resistance, because there's just more things to bump into. Since resistance is coming from the fact that the electrons are kind of scattering off these positive nuclei inside the metal, inside this weird sea of electrons, then it makes sense that by having a longer wire, we just have more of them to hit, and so therefore we hit more of them, and it just is harder to push the electron through. But the area might be a little surprising. Why is it that a wider channel gives you lower resistance? And fundamentally here is because there are just many paths an electron can take. So if there's sort of a traffic jam up ahead because some things are scattering off positives, right? So we have like positive, 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 whatever. And we have an electron coming through and scattering. And then we have some other electron. That electron can just kind of go around the collision. There's just more places to go if the thing is wider. It's important to understand that Ohm's law, quote unquote, is not a fundamental law of nature. It's a feature of a certain class of metals, a broad class, but finite. In metals and some other materials, the resistance remains constant. All right, that's the key bit. The current and voltage are always proportional no matter what their value. No matter what. Ooh, very bad. No matter what their value. Sorry about that. Materials that obey that are called ohmic. All right, metals are generally ohmic, but carbon is generally not, and so on. Diodes are not. Lots of things, in fact, are not. For ohmic materials, if I plot I versus V, I get 1 over the slope is the resistance, but for non-ohmic materials, I don't get that. It's also important to understand that we really end up with that the resistance is really, right, is always V over I. It's not a derivative. It's not a slope. If we were starting over from scratch, doing all the physics from zero, then we probably would have made it a slope. But that's not how it was defined by engineers long before they thought they were using calculus in this. And we sort of have to use that as just this gross, take the current voltage difference and divide by the current at this moment, and that gives you the resistance. All right, the current through a wire as measured in potential difference is measured as potential difference is varied. What is the resistance? Well, because we have that V equals IR, then I equals 1 over R times V, which means 1 over R is the slope, or R is 1 over the slope. Since we do, it looks like, so equals 1 over 50 amps over 1 volt. So 1/50th volt per amp, or 0.02 ohm. Metals and other conductors tend to be ohmic, but batteries, diodes, incandescent bulbs, and some other devices are non-ohmic. We have to keep that in mind. Wires are generally made of good conductors, and we will generally work in the area of the ideal wire approximation, wherein wires have a resistance of 0 ohms and insulators have a resistance of infinite ohms. Because wires have such low resistance, circuits made up of only wires would draw a huge current, and usually we play resistors in these circuits to limit the draw. Otherwise, you get a short. What resistor would have a 15 milliamp current if connected across the terminals of a 9 voltage battery? Well, V equals IR. So R equals V over I equals 9 volts over 15 times 10 to the minus 3 amps. So 9/15 of 1,000 ohms. This is 600 ohms.